Today we are continuing with the rate and reversible reactions. Last time we had a reversible reactions topic. We are continuing with this. Today we are going to put two examples of the reversible reactions, right? We are going to apply these reversible reactions on the different two types of the reactions. One is Haber and the other one is contact process, right? So first you have to give heading Haber process. Haber process. Okay, in Haber process, it is used for the manufacture of ammonia on a large scale. Large scale means industrial method. When we have to prepare ammonia, NH3 on a large scale, on an industrial method, we can use this process known as Haber process. What happens in the Haber process? Look, nitrogen gas reacts with the hydrogen gas in a reversible reaction to form ammonia, which is a gas. This reaction is known as Haber process. Okay? This reaction is known as Haber process. And this is how ammonia is. Ammonia is a very useful chemical. You know, it is used for the manufacture of fertilizers. It is used for the manufacture of explosives, right? A lot of uses for ammonia. And fertilizers are, very, very useful substances. They are being used throughout the world for the better growth of the crops because they provide nutrients to the crops. So ammonia is key compound which is used for the preparation of fertilizers. Now, how the ammonia is prepared in the industry on a bigger scale, the barrels of ammonia, this is the reaction in which nitrogen and hydrogen is mixed in a container to form ammonia. But the reaction, as you can see, is what? It is a reversible. So first of all, we have to tell you the sources of the reactants, and then we can move on to the reaction conditions. Nitrogen. Nitrogen obtained. We all know nitrogen is a gas. By the fractional distillation. Liquefied air. So nitrogen is obtained by the fractional distillation of liquefied air. Air, contains 78% of nitrogen. So you have to liquefy the air and then undergo the process of fractional distillation. Fractional distillation, where the difference in the boiling points separates the things all together, right? So you take the air, liquefy it, undergo the fractional distillation, you get the nitrogen. Second thing is the hydrogen. Hydrogen gas, which is needed in this process, is obtained by the cracking. Long chain hydrocarbons. I'll explain in the next part when we'll be doing organic. So at this moment, you just need to keep in mind where the hydrogen is obtained by the cracking of long chain hydrocarbons. Cracking is the phenomena which is happening in the petroleum industry, where they convert the less useful chemicals, the lubricating oil and diesel and all that, into more useful. Okay, so these are the two sources of nitrogen. Now we have the nitrogen and oxygen, hydrogen. We mix them to form ammonia. But when we mix them to form ammonia, you see the reaction is what? Reversible. And if I write the delta H of this reaction here, minus 92 kilojoule per mole, which shows that the reaction is what? Exothermic. So in the industry, if we go as an advisor, we have to suggest the reaction conditions to the person so it can get the maximum yield of ammonia, right? So now we have to suggest the conditions where the equilibrium has to go in which direction? Forward direction, right? So what are the reaction conditions for this? So please give heading reaction conditions. So the reaction conditions which are suggested, number one, temperature is 450. Okay. Pressure. Okay, first let me discuss the temperature. Why 450? That's the point. Why 450? You have to discuss it. Now look at this reaction. This is the reaction that is taking place here in a closed container. As we discussed, we want the equilibrium to shift in which direction? Forward as much as possible, so we can have the maximum yield of ammonia. The reaction is exothermic. So it means which temperature favors to go to the forward direction? We discussed it yesterday. Is exothermic, releasing energy going forward. So what should be the temperature? It should be as low as possible, because low temperature shifts the equilibrium forward to the side where it is exothermic. So we should not have a 450 temperature then. It should be lower than 100. But what's the problem? Lowering temperature lowers the speed. If we suggest somebody in the industry that, okay, lower the temperature, your equilibrium will go forward, you will have more ammonia. But he'll have obviously more ammonia, but in more days. Because the reaction speed is so slow, the 1 barrel of ammonia which he was making in 1 day, now it takes 3 days. The labor cost, the expensive, the electricity, everything goes up. So we can't suggest it. So we have to suggest him a temperature which is reasonable. So although lowering temperature gives the better yield of ammonia, but it lowers the speed. So we suggested a compromised temperature. Because if we increase the temperature, then what's the problem? Increase in temperature will shift the equilibrium backwards. That will decrease the yield of ammonia. So we found a temperature which is compromised, and that is 450, where the yield is also good and the speed is also reasonable. Okay, so please write down why temperature 450, they ask you. So what you will write, low temperature gives better yield of ammonia. Low temperature gives better yield of ammonia as reaction is exothermic. In forward, and lowering temperature shifts equilibrium right hand side. But problem क्या है? It lowers speed of a reaction. Hence, what to do? Hence, a compromised temperature of 450 degrees Celsius is used. Number two, pressure. Pressure for this reaction is 100 to 200 atm. Okay, look at this. What do you suggest about the pressure? Should be high, should be low for the better yield of ammonia? Where for the pressure you have to see the number of moles. 2 moles on this side for the ammonia, and how many moles on this side? 4 moles on this side. So what do you think? High pressure gives the equilibrium forward, giving better yield of ammonia. But what's the problem? Why we did not have 1000 or 2000 atm pressure, which is high? High pressure is actually a process which is expensive to achieve. For example, I'm just using the numbers to explain it, not the original numbers. Let's say we spent 1000 rupees to get a high pressure. Although the yield of ammonia got very, very best, but you know what, the ammonia when we went to sell in the market, it was just 100 rupees. So there's no point spending 1000 to get 100 rupees. The yield of ammonia that got better, that was only 100. So that's why we cannot suggest him to increase the pressure just like that. So therefore, 100 to 200 atm, again, a kind of pressure which is not expensive to achieve and gives the better yield of ammonia. So please write down high pressure gives better yield of ammonia. High pressure better yield of ammonia, but it is why better yield of ammonia? Let me explain it. Sorry. Better yield of ammonia as less number of moles of gases on the product side and equilibrium shifts to the right hand side by increasing pressure. Problem क्या है? But it is to achieve. Hence, 100 to 200 atm use. 100 to 200 atm is used.
सर ऊपर के ना स्क्रीनशॉट लेना.
Okay.
जूम आउट कर दें बंदे सर.
अभी ठीक है? The third condition
sir.
is catalyst. And then we have to add powdered iron as a catalyst. Powdered again, increases the surface area in contact. Okay? Right. So this is how the Haber process is used to manufacture the ammonia, and these are the sources, and this is how the uh, the reaction conditions are set. Okay. Now give another heading: sulfuric acid. There is another application of the reversible reaction in the preparation of sulfuric acid. Now, sulfuric acid is a very widely used chemical. As I told you, that ammonia is used for the manufacture of fertilizers and explosives. Sulfuric acid is also very useful chemical. It is actually so much useful that when you have to check how much industry of a country is progressing, you have to check the use of sulfuric acid daily. How much a country is using the sulfuric acid on daily basis. That gives you the idea. It is almost used in every industry.